In a series of videos, we're going to be showing that the functions e to the negative alpha k squared times t multiplied by e to the power of ikx are solutions to the uniaxial time-dependent heat diffusion equation. So with no heat generation for a time-varying temperature profile in a uniform bar that is 50 meters in length with thermal diffusivity of 1 meter squared per second, and it will be simulated computationally through finite differences with a spatial step of 1 meter. So we will also be deriving an explicit differencing scheme for calculating the time-varying temperature profile, coding this derivation in Python and plotting our results, applying the von Neumann stability analysis to our derivation and show the requirement for stability, and we will also be deriving the Crank-Nicolson finite differencing scheme for the heat diffusion equation and showing that it has no stability constraints, and we will be implementing the Crank-Nicolson method and plot the temperature profile as a function of time. So written here are all of the equations we'll be using for these videos. We've got the heat diffusion equation here and Euler's formula here. So first we're going to start off with the von Neumann stability analysis to show that the function is, e to the negative alpha k squared times t times e to the power of ikx are solutions to the uniaxial time-dependent heat diffusion equation. And so we first write the partial differential equation for time-dependent heat diffusion in a uniaxial material with no heat generation. So we have the derivative of temperature with respect to time is equal to the thermal diffusivity times the second derivative of temperature with respect to position. And this is our heat diffusion equation. And remember, we also have Euler's identity or Euler's formula, which is e to the power ix equals cosine x plus I sine x. So solving for t, we end up getting t equals e to the power of ikx multiplied to the power of e to the power of negative alpha k squared times t. K in this is an integer and not the thermal conductivity. Substituting this new equation into our heat diffusion equation to check if this satisfies our partial differential equation, we ended up getting negative alpha k squared times e to the power of negative alpha k squared times t multiplied by e to the power of ikx equals alpha times e to the power of negative alpha k squared times t, and then this is multiplied by I squared k squared times e to the power of ikx. The first part of this equation was derived by substituting our expression for temperature into the heat diffusion equation and took the derivative with respect to time. And then the second part of this equation was um, derived by substituting the expression for temperature in, but we took the derivative 2 times with respect to x. So I is an imaginary number, so it's just a negative 1 squared. So simplifying the right side of the expression, we get negative alpha k squared times e to the power of negative alpha k squared times t multiplied by e to the power of ikx. And the left side is equal to the right side. Therefore, the expression for t for any value of k is a solution to the partial differential equation. And now we've shown that e to the power of negative alpha k squared times t multiplied by e to the power of ikx are solutions to the uniaxial time-dependent heat diffusion equation. Thank you. And we will be starting part 2 momentarily. This is part 2, where we derive an explicit forward differencing scheme for calculating the time-varying temperature profile. And for this, we are going to start at a partial change in temperature over a partial change in time is equal to alpha times the change in temperature over a change in position squared. And this is our heat diffusion equation. So we can rewrite this to be t at position j at n plus 1 minus t at position j at n divided by delta t equals alpha times t at position j plus 1 at n minus t at position j at n divided by delta x. And then we subtract t at position j at n minus t at position j minus 1 at n divided by delta x, and that is also divided by delta x. And alpha in this is thermal diffusivity, delta t is change in time, delta x is the change in space on the bar, and cam T is the temperature, J is the current space on the bar, and N is the current time. So I just put in parentheses to make it easier, and next we're going to evaluate this equation to put T at n plus 1 on one side and T at n on the other side. So we end up getting T at position j at n plus 1 equals T at position j at n plus alpha times delta t times T at position j plus 1 at n minus 2T at position j at n plus T at position j minus 1 at n, and then this is divided by delta x squared. I'm just going to add in parentheses right here to make it easier. And to simplify this a little, we make the evaluation of r. So we have r equals alpha times delta t divided by delta x squared. And so then we get t at position j at n plus 1 equals t at position j at n plus r times t at position j plus 1 at n minus 2t at position j at n plus t at position j minus 1 at n, and there we go. This is our equation for calculating the next temperature at the next time increment. Thank you.